Switch. Let's go.
Done hard.
Big round, serious always.
Let's go. Let's go. Let's go. Multidimensional. Grids and data. PMPP book. Let's go. What else? What else? Okay. So my microphone is in here, so I should be a little bit. Yeah. So we stopped here in chapter 3, 3.3, image blur application, complex kernel. Yeah, so wow. Somebody just followed me 7 days ago. Yeah, let's read it. So in this chapter 3 before, we just figured out how these blocks and threads are working together, and also like, you know, you should use these block IDs, block index and block dimension and thread index to figure out how to create your kernel function. So this is like a kernel function to figure out how your threads are gonna work and which threads are gonna work. So some of them are gonna be idle instead of, you know, instead of using your resources. So right now it was an application about vector addition, and it was an easy application. So right now we're gonna figure out how to use these kernel processing, kernel functions, and parallel programming in image blur function or image blur application. So let's read it together. We have studied vec at kernel and color to grayscale conversion, in which each thread performs only a small number of arithmetic operations on one array element. These kernels serve their purposes well to illustrate the basic Q-C program structure and also data parallel execution concepts. Wait a minute. At this point, the reader should ask the obvious question: do all threads in Q-C programs perform only such simple and trivial operations independently of each other? So we are focusing on independently. Each threads are broken independently, not depending on each other. That's how parallel programming works, and why this is such a big optimizations in your application. So the answer is no. Okay. So, in real QRC programs, threads often perform complex operations on their data and need to cooperate with each other. Okay. So they can cooperate with each other, but so I was talking about more like a data parallelism, and like data parallelism, you are making data independent to each other, and but it says and need to cooperate with each other. For the next few chapters, we are gonna work on increasingly complex examples that exhibit these characteristics. We will start with an image blurring function. Image blurring smooths or abrupt variation of pixel values while preserving the edges that are essential for recognizing the key features of the image. Figure 3.6 illustrates the effect of image blurring. Simply stated, we make the image blurry to humanize. A blurred image tends to obscure the fine details and present the big picture impression or the major thematic objects in the picture. In computer image processing algorithms, a common use case of image blurring is to reduce the impact of noise and granular rendering effects in an image by correcting problematic pixel values with the clean surrounding pixel values. A common use case is to reduce the impact of noise. Reducing the impact of noise, and granular rendering effects in an image by correcting problematic pixel values with the clean surrounding pixel values. Okay. In computer vision, image blurring can be used to allow edge detection and object recognition algorithms to focus on thematic objects rather than being bogged down by a massive quantity of fine-grained objects. In displays, image blurring is sometimes used to highlight a particular part of the image by blurring the rest of the image. Okay. Mathematically, an image blurring function calculates the value of an output image pixel as a weighted sum of a patch of pixels encompassing the pixel in the input image. As we will learn in chapter 7 convolution, the computation of such weighted sums belongs to the convolution pattern. So this is our image, and after the our conversion function, it's gonna be blurred as you can see in the right. We will be using a simplified approach in this chapter by taking a simple average value of the n times n patch of pixels surrounding and including our target pixel. Okay, to keep the algorithm simple, we will not place a weight on the value of any pixel based on its distance from the target pixel. In practice, placing such weights is quite common in convolution blurring approaches such as Gaussian blur. Okay. Figure 3.7 shows an example of image blurring using a 3x3 patch. When calculating an output pixel value at row column position, we see that the patch is centered at the input pixel located at the row column position. Also, by the way, I should just put the Safari, to which I should just send the link. I should in the Twitter. Just learning multi-dimensional grid and data. Programming parallel massively parallel processors. Let's go. Also, I should send in the Mary's channel. In the content creation. Okay, let's continue. Figure 3.7 shows an example of image blurring using a 3 to 3 patch. When calculating an output pixel value at okay. That patch is centered at the input pixel located at the row call position. The 3 times 3 patch spans 3 rows and 3 columns. For example, the coordinates of the 9 pixel for calculating the output pixel at okay. Figure 2.8 shows an image blur kernel, similar to the storage that was used in color to grayscale conversion. We use each thread to calculate an output pixel. That is, the thread to output data mapping remains the same. Thus, at the beginning of the kernel, we see the familiar calculation of the call and row indices, lines 3 and 04. We also see the familiar if statement that verifies that both call and row are within the valid range according to the height and width of the image. Okay. Only the threads whose call and row indices are both within value ranges are allowed to participate in execution. So it says to calculate this, for example, this pixel, you need to get all these pixels and you should get weighted sum of these 9 pixels. Each output pixel is the average of a patch of surrounding pixels and itself in the input image. So this is our kernel, an image below kernel. Okay, so you are getting the column and row in here with this x and y of block index, block dimension, and thread index. And then what is w? If column smaller than w and row smaller than height, for get average of the surrounding blur size multiplied by blur size box. For int blur row minus blur size, blur size plus 1, blur row plus plus. For int blur column equals to minus blur size. So there are two for loop in here. One of them is go towards the rows and one of them is go through the blue columns. in current row equals to row plus blue row. Okay. Verify we have a valid image pixel. If current row is bigger than 0 and current row smaller than height and current column bigger than 0 and current column smaller than width, sorry, and pixel value plus equals to in current row times w plus current column plus pixels. Keep track of number of pixels in the average. Write our new pixel value order. So this is like going through all the pixels around your. So there's blur size. I guess, yeah, in here it explains already. Yeah, let's go. As shown in figure 3.7, the colon row values also give the center pixel location of the patch of input pixels used for calculating the output pixel for the thread. The nested for loops in figure 3.8, lines 10 and 11, iterate through all the pixels in the patch. So one patch probably 9. Is it 9 pixels or not? Yeah, maybe. Maybe. We don't know. We assume that the program has a defined constant blur size. The value of blur size is set such that blur size gives the number of pixels in each side. The patch and 2 times blur size plus 1 gives the total number of pixels across one dimension of the patch. Okay, so the patch, for example, for a 3 times 3 patch, blur size is set to 1, whereas for a 7 times 7 patch, yeah. So for example, take as this 3 to 3 pixels, and if your, what is that, blur size, yeah, if your blur size is 1, there is just one pixel at each direction, the surrounding of your pixel. And if it's gonna be 2, there will be 2, there will be probably 25 pixels. And if it's gonna be 3, so you can calculate with this equation, like 2 times blur size plus 1. Okay, the outer loop iterates through the rows of the patch. For each row, the inner loop iterates through the columns of the patch. Okay, in our 3 times 3 patch example, the blur size is 1. For the thread that calculates output pixel 2550 during the first iteration of the outer loop, the current row variable is row minus blur size equals to 24. Thus, during the first iteration of the outer loop, the inner loop iterates through the patch pixels in row 24. Okay. The inner loop iterates from column if column size is 50. If your column is fifth column, 15th, not 15th, fifth. Yeah, fifth column. So your inner loop iterates column 49 to 51. Using the current column variable. Therefore, the pixels that are processed in the first iteration of the outer loop are 24, 49, 24 fifth, and 24 51. The reader should verify that in the second iteration of the outer loop, The inner loop iterates through the through pixels 25, 49, 25, 50, 25, 51. Yeah, take this as an example. Handling boundary of conditions for pixels near the edges of the image. Yeah, so for example, in the edge of the image, these 3 or these like 5 pixels are blank. There is no data. So how we are going to handle the boundary conditions? And also let's see, so we are in the 61st page. Yeah, 67 is finished. So since I have school tomorrow, I'm probably gonna be I'm gonna finish this chapter and I'm gonna go to sleep. But normally I want to read chapter 4 also in here. Chapter, what is it about? Computer architecture and scheduling. Okay, sounds cool. Anyway, yeah. Line 16 uses the linearized index of current row and current column to access the value of the input pixel visited in the current iteration. It accumulates the pixel value into a running sum variable pixel value. Line 17 records the fact that one more pixel value has been added into the running sum by incrementing the pixel variable. After all the pixels in the patch have been processed, line 22 calculates the average value of the pixels in the patch by dividing the pixel value. I'm just gonna check it out if there is any message in the chat. How can I see the chat in the mobile? Mobile. Okay, nobody is here, but that's totally okay. That's totally okay for me. After all the pixels in the patch have been processed, line 22 calculates the average value of the pixels in the patch by dividing the pixel value by the pixels value. It uses the linearized index of row and col to write the result into its output pixel. Line 15 contains a conditional statement that guards the execution of lines 16 and 17. For example, in computing output pixels near the edge of the image, the patch may extend beyond the valid range of the input image. This is illustrated in figure 3.9, assuming 3.3 pages. In case 1, so we are talking about this case. In case 1, the pixel at the upper left corner is being blurred. 5 of the 9 pixels in the intended patch do not exist in the input image. Yeah. In this case, the row and col values of the output pixels are 0 and 0 respectively. During the execution of the nested loop, the current row and current column values for the 9 iterations are -1, -1, -1, 0, -1, 1, 0, -1, 0, 0, 0, 1, 1, -1, 1, 0, 1, 1. During the execution of the nested loop, the current row. Okay. Note that for the 5 pixels that are outside of the image, at least one of the values is less than 0. The current row is smaller than 0 and current column is smaller than 0 conditions of the if statement catch these values and skip the execution of lines. Ah, okay. So there's our, where is it? Yeah, it's in here. So in here we are verifying that we have a valid image pixel. with this current row minus smaller than height, and current column is smaller than width. And if one of them if no, not in here, sorry, current row is bigger than 0 or equals to 0, or current column is bigger than 0. So if one of them is not right, if one of them is blank, or if one of them is not exist, so in this case this one is not exist, this not is not exist in one direction of it's not exist in y direction, but it exists in x direction. So if one of them is not exist, then our function is just have these conditions to skip these values and catching these values and skip the execution. As a result, only the values of the four valid pixels are accumulated in the rounding sum variable. The pixels value is also correctly incremented only 4 times so that the average can be calculated properly at line 20. The reader should work through the other cases in figure 3.9 and analyze the execution behavior of the nested loop in blue kernel. Note that most of the threads will find all the pixels in their assigned 3 patch within the input image. They will accumulate all the 9 pixels. However, for the pixels on the 4 corners, the responsible threads will accumulate only 4 pixels. Yeah, I guess my camera is dirty. I just checked in the mobile. Okay, so the reader should work. Okay, analyze the execution behavior of the nested loop in blue kernel. Note that most of the threads will find all the pixels in their assigned. They will accumulate all the 9 pixels. However, for the pixels on the 4 corners, the responsible threads will accumulate only 4 pixels. For other pixels on the 4 edges, the responsible threads will accumulate 6 pixels. Accumulate 6 pixels. These variations are what necessitates keeping track of the actual number of pixels that are accumulated with the variable pixels. Only 4 pixels. So it says in this case, in these edges, these 4 pixels are just accumulated, the weighted sum. Or if it's in the it's not in the corner, but it's in the edge. So it's this one is corner, this one is edge. So if it's in the edge, these 3 pixels are not considered. These 6 pixels are just accumulated or getting summed. These versions are what necessitates keeping track of the actual number of pixels that are accumulated with the variable fixed. Okay. So matrix multiplication, matrix multiplication, or matrix multiplication in short, is an important component of the basic linear algebra subprogram standard. See the linear algebra function sidebar. It's the basis of many linear algebra solvers, such as LU decomposition. It's also an important computation for deep learning using convolutional neural networks. Yeah, matrix multiplication is so important. I'm also gonna just write it in here. Even though I'm not good at linear algebra, it's so important. Yeah. So it's gonna be discussed in detail in chapter 16, deep learning chapter. So this is the sidebar, I guess. Yeah, it should be sidebar. Linear algebra operations are widely used in science and engineering applications. In the basic linear algebra subprograms, BLAS. As far as I know, there is CUDA BLAS. Safari. Let's see. CUDA BLAS. QBLAS. QBLAS. Yeah, QBLAS. Now let's check it out, the documentation. So yeah. I don't know when, but I need to read these documentations of CUDA to completely understand what is going on behind the optimizations of deep learning. A de facto standard for publishing libraries that perform basic linear algebra operations. There are three levels of linear algebra functions. Three levels. As level increases, the number of operations performed by the function increases. Level 1 function performs vector operations of the form y. Y equals to alpha x plus y, where x and y are vectors and alpha is a scalar. Our vector addition example is a special case of a level 1 function with alpha equals to 1. So we are adding 1 to our vector in this case. So level 2 functions perform matrix vector operations of the form y equals to alpha ax plus beta y, where A is a matrix, x and y are vectors, and alpha and beta are scalars. We will be studying a form of level 2 function in sparse linear algebra. Yeah. So the first level is vector addition. The second level is what kind of addition is it? So it's more like a so it's not just vector operation. It's matrix vector operations. Yeah, the first one was just vector operation. We will be studying a form of level 3 functions perform matrix operations in the form of C equals to alpha AB plus beta C, where AB and C are matrices and alpha and beta are scalars. Or it's not matrix vector, but it's matrix operation, multiplication. So yeah, these BLAS functions are important because they are used as a basic building blocks of higher level algebraic functions such as linear system solvers and eigenvalue analysis. As we will discuss later, the performance of different implementations of BLAS functions can vary by orders of magnitude in both sequential and parallel computers. Matrix multiplication between an I and G, I rows by G columns, matrix M and a J times K matrix, and produces an I times K matrix P, where a matrix multiplication is performed. Each element of the output matrix P is an inner product of a row of M and a column of N. We will continue to use the convention where P row call is the element at the row position in the vertical direction and the called position in the horizontal direction. As shown in figure 3.10, P row call, the small square in P is the inner product of the vector formed by the row of M, shown as a horizontal strip in M, and the vector formed by the column of N, shown as a vertical strip in N. So it sounds complicated. I don't understand it. So we should check it out, figure 3.10 to understand it. But let's finish it. The inner product, sometimes called the dot product of two vectors, if is the sum of products of the individual vector elements. That is row col. This is sum of m row k times n col k and k col for k equals 0, 1 and da 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 da, da with a minus 1. So yeah, so this is matrix multiplication using multiple blocks by tiling pay. For example, in figure 3.10, assuming row 1 and column 5, 1005, okay, 10, 1005, 11, okay, I don't understand it. I don't understand it right now. To implement matrix using Coda, we can map the threads in the grid to the elements of the output matrix P with the same approach that we used for color to grayscale conversion. That is, each thread is responsible for calculating one P element. The row and column indices for the P element to be calculated by each thread are the same as before. But before that, I need to understand. Anyway, with this one-to-one mapping, the row called thread indices are also the row and column indices for their output elements. Figure 2.11 shows the source code of the kernel based on this thread to data mapping. A matrix multiplication kernel using one thread to compute one P element. Int row, so you're defining row and column, and then if row smaller than width and column is smaller than width, float P value is equals to 0. So there is one for loop in here. Int k is equals to 0, k smaller than width, plus plus k, P value plus equals to m, row times width plus k times n, k, so that there m, n, n. I'm not in productive mode right now, so it's a little bit hard to understand for me. Not because matrix multiplication is hard, but because this syntax of C is a little bit hard to understand. So if there is some kind of diagrams or you know plots, yeah. So for example, execution. it would be easier to understand for me. Let's continue. So sometimes I'm not understanding, but somehow I'm continuing because in later, so for example, maybe I'm not understanding because the explanation is here, or maybe explanation is in another page. So let's continue. So the reader should immediately see the familiar pattern of calculating row and call and the if statement testing if row. Okay, I'm definitely familiar with these things. These statements are almost identical to their counterparts in call to grayscale conversion. The only significant difference is that we are making a simplifying assumption that matrix multiplication kernel needs to handle only square matrices. So we replace both width and height with width. This thread of data mapping effectively divides pay into tiles, one of which is shown as a light colored square in figure 3.10. So pay M and okay, I got it. So I was just saying why I'm not understanding because these M and N are the just two matrix, and this pay is the multiplication of them, the result of them. So there's like one block, and inside the block there are many threads, and each thread is dependent to column in N and row in M. That's why. Yeah, got it. It was pay into tiles, one of which is shown as a light colored square. I was just assuming that these are like more like a, you know, blocks. So since that there are block with in here, I was just assuming these are all blocks in parallel programming. So these are not blocks. These are just matrices. And in here it just shows it's gonna be calculated inside of block. So these are not blocks. Anyway, each block is responsible for calculating one of these tiles. Okay, we now turn our attention to the work done by each thread. Recall that P row call is calculated as the inner product of the row and M row of M and the called column of N. Yeah, that's right. In figure 3.11, we use a for loop to perform this inner product operation. Before we enter the loop, we initialize a local variable p value to 0. Okay. Each iteration of the loop accesses an element from the row of M and an element from the called column of N. Multiplies the two elements together and accumulates the product into p value. Let us first focus on accessing the M element within the for loop. M is linearized into an equivalent 1D array using row measure order. That is, rows of M are placed one after another in the memory space, starting with the 0th row. Therefore, the beginning element of row 1 is M1 times width, because we need to account for all elements of row 0. In general, the beginning element of the row is row times width. Since all elements of the row are placed in consecutive locations, the keyed element the keyed element of the row is at row times width plus k. Okay, this array offset is what we use in figure 2.11. We now turn our attention to accessing n, as is shown in figure 3.11. The beginning element of the called column is Accessing the next element in the column requires skipping over an entire row. This is because the next element of the same column is the same element in the next. Okay. This is because the next element of the same column is the same element in the next row. Therefore, the kth element of the called column is an k times width plus call. After execution exits the for loop, all threads have their p element values in the p value variables. Each thread then uses the 1D code index expression row with call to write its p element. Again, this index pattern is like that used in the Calder grayscale conversion kernel. We now use a small example to illustrate the execution of the matrix multiplication kernel. Figure 3.12 shows a 3 times 3 pay with block width 2. Yeah, in here. Although such small matrix and block sizes are not realistic, they allow us to fit the entire example into one picture. The pay matrix is divided into 4 tiles and each block calculates 1 tile. We do so by creating blocks that are 2 times 3 two arrays of threads with each thread calculating 1 p element. In the example, thread of block calculates p00, whereas thread 00 of block 1 2 calculates p2. Draw and call indices in matrix multiplication kernel in the identified. It's really hard to read this book in the live stream. Yeah, because I'm trying to read everything. Normally, when I'm reading a book, I'm always reading everything to understand correctly. Otherwise, sometimes I'm not understanding it. And yeah, this is just a reflection. The row index also identifies the row of M, and the call index identifies the column of N as input values for the thread. Figure 2.13 illustrates the multiplication actions in each thread block. For the small matrix multiplication example, threads in block produce 4 dot products. Draw call indices of thread 1 0 in block 0 0, 0 times 0 plus 1, 0 times 0 plus 0, respectively. So, yeah, this is y direction, this is x direction. That's why 0 times 0 plus 1. And for the 0 0 0 times 0 plus 0, respectively. The thread thus maps to P10 and calculates the dot product. Let us walk through the execution of the for loop of doing iteration row with for So if and k times width plus column. Therefore, the input element accessed are m0 and n0, which are the 1D equivalent of m00 and n00. Note that these are indeed the zeroth elements of row 0 of m and column 0 of n. Yeah. During iteration 1, and k times width. Therefore, we are accessing m1 and n4, which are the 1D equivalent of m01 and n10. These are the first elements of row 0 of m and column 0 of n. During iteration 2, it changed m2 and n8. Therefore, the elements accessed are the 1D equivalent of m02 and 20. Finally, during iteration 3, these are blocks. Every one of them is threads, and block width is equals to 2. Yeah, all of the M0 and all of the N0. No, all of the N columns 0, 1, 2, 3. All of the M1 and all of the columns from all of the rows from N in the first column. Oh my god, let's finish this book. Let's finish chapter 3. It's so fucking hard right now. The 1D equivalent, 2D equivalent. We have now verified that the for loop performs the inner product between the zeroth row of M and the zeroth column of N for thread in block. After the loop, the thread writes, which is pay 0. This is 1D equivalent. So thread in block successfully calculated the inner product between the and deposited the result. Okay, deposited. We will leave it as an exercise for the reader to hand execute and verify the for loop for other threads in block 0 or in other blocks. Since the size of a grid is limited by the maximum number of blocks per grid and threads per block, the size of the largest output matrix P that can be handled by matrix multiplication kernel will also be limited by these constraints. In the situation in which output matrices larger than this limit are to be computed, one can divide the output matrix into submatrices whose sizes can be covered by a grid and use the host code to launch a different grid for each submatrix. Okay, so we can use these different grids for each submatrix. Alternatively, we can change the kernel code so that each thread calculates more pay elements. We will explore both options later in this book. Okay. Summary. Let's summarize chapter 3. What we learned in multidimensional grid and data. CUDA grids and blocks are multidimensional with up to 3 dimensions: X, Y, and Z. The multidimensionality of grids and blocks is useful for organizing threads to be mapped to multidimensional data. This is important. If we have multidimensional data, like if in the data set we have X, Y, and Z, we can map these map this data to the threads or blocks or grids. The kernel execution configuration parameters define the dimensions of a grid and its blocks. Unique coordinates in block index and thread index allow threads of a grid to identify themselves and their domains of data. It's the programmer's responsibility to use these variables in kernel functions so that the threads can be properly identified. The threads the portion of data to process. So it's our job, programmers' responsibility, to handle these multidimensionality with threads. So our threads can work on it and work on it properly. When accessing multidimensional data, programmers will often have to linearize multidimensional indices into a 1D offset. The reason is that dynamically allocated multidimensional arrays in C are typically stored as 1D arrays in row major order. We use examples of increasing complexity to familiarize the reader with the mechanics of processing multidimensional arrays with multidimensional grids. These skills will be foundational for understanding parallel patterns and their associated optimization techniques. Okay. So there are exercises. Of course, I'm not gonna do exercises in here live because I'm bad at it. Probably I'm gonna screw it up. That's why we are passing right now. Although I did exercises before, of course I'm gonna do exercises for the chapter 3, but I'm not gonna do on live. So yeah, that was it. That was it. These are exercises, and we are in here. Chapter 4: Compute Architecture and Scheduling. We're gonna read it maybe tomorrow, maybe other day. I don't know. That's it for me. Also, maybe we can read this documentation live because, you know, live stream makes me accountable. That's why I'm doing live. And also, I started reading this book called Operating System Concepts. Where is the cover? Yeah, the Dragon Book from Abraham Silverskash. Skash. I don't know how to pronounce it. So I just read it, the contents, preface, etc., overview, introduction, and where was I? Yeah, I was in here. Interrupts and overview. You know, I'm reading slow, but since I have operating system class in the school, and I also started reading this book called Linux from Scratch. Yeah, I'm in the part 1 introduction. I just installed Arch Linux on my ThinkPad, and I'm gonna build my own Linux based on Arch, and yeah, it's all already 1 a.m. I need to brush my teeth and do some skincare. Just kidding. Just kidding, man. So you know, there's operating systems lesson tomorrow, and I need to wake up at 7:30. Of course, this is just my time to go. I need to wake up at 6:30 or something like that to, you know, to wake up. So yeah, these are these this book is just teach you how to build and compile applications, compile everything from scratch while you are building your own distribution. And yeah, that was it from me for today. So I'm just gonna stop it. And yeah, have a good one, everybody. I'm just gonna upload this video to the YouTube. Bye.